So let's take a look at the feasibility of learning that we hinted at the last section. So if we think about conjunctive hypotheses, they're basically putting together constraints in an additive way and saying that somebody likes coffee, maybe they like it with evaporated milk and with ice, right? But if we think about other possible hypothesis space, for example, a disjunctive space, which allows you to express preferences that are disjoint, right? Having an or constraint. I like coffee that's hot or tea that's cold, for example. Then we can cover that in the conjunctive hypothesis space. We might want to try to learn something that's unbiased, right? Not making a particular assumption about the hypothesis space, saying, I can learn whatever type of concept you want me to recover, okay? So we want to choose a hypothesis set, right, the script H, that can express every single teachable concept, meaning all of the different hypotheses that we could have. Let's think about this a second. Let's say we have 6 different attributes, right? So we're going to write that down. 6 attributes, okay? How many different ways can we set these 6 attributes? Well, each of these different attributes has a binary value, right? So, depending on how I switch these on and off, I will have a total of 2 to the 6 different ways of setting that value, okay? So each of these 2 to the 6 are going to be the number of data items in X, right? This is the space of data items in X. But if I think about the function that I could create, meaning the teachable concepts, all the valid concepts there are, for each of these 2 to the 6 strings, I can express either a positive or a negative value, right? I prefer, I don't prefer. So how many teachable concepts are there in the case where we have 6 attributes that all are Boolean? Okay, our case is actually not like that. We have one attribute that is have 3 choices, right? But let's just simplify it for this, right? Then hopefully you can understand that this is going to be a power set. So I'll have 2 to the 6 items that are going to be all of the possible hypotheses that can be generated for this case where I have 6 binary attributes. Okay, so I have 2 to the 6 data items, but I have 2 to the 6 different concepts that I can create from this. Okay, now that's great. That's a very, very, very large space, and that becomes very difficult to learn from, right? Because basically, for any possible drink, any one of these 2 to the 6 data items, I could decide to prefer it or decide not to prefer it. So I wouldn't actually know ahead of time for any hypothesis whether it's going to mimic the target function, because I can set the target function any way I want. I can ask my friend and say, well, I like it or I don't, right? So we'll need training examples for all of the possible data items, for all 2 to the 6 data items, in order for us to converge to the target concept. Okay, so that's bad news. That basically means we need the entire target function in order to learn the target function. Okay, so that's not going to work. We cannot actually classify any new unobserved input instances unless we actually have the data item to learn the label from. Okay, so this is a problem. If we have this set of hypotheses, we can't learn from it. We're going to have to make some certain assumptions in order for the learning problem to be tractable. Okay, so for us to classify new unobserved examples, there must be some power in the model to infer preferences over unobserved examples, although it definitely could be wrong, right? Because we are assuming in some ways some structure of the input that's not actually there. We made that assumption in the conjunctive hypothesis space, where we said we believe that people are going to express preferences that are additive rather than disjoint. Right? So we can see that actually, if we don't make any commitment a priori to a certain way of representing the hypothesis, there's actually no way that we can choose the right target function. right? Because as we said before, if I give a particular data item, a particular drink out of those 6 attributes, it's clear that the target function could either prefer or not prefer that drink, right? So without any prior assumptions, we won't be able to make that commitment, and we won't be able to generalize, okay? So every single machine learning algorithm out there is going to have this trait called inductive bias, very important, okay? It's basically the prior assumptions that a particular algorithm is going to make in order for us to make the learning feasible, okay? So we can actually nicely use inductive bias is in a way to measure how much bias is there, and then we can choose or order the different learning algorithms according to how much bias they induce. Of course, the more bias there is in an algorithm, the stronger its capability to generalize, but the more assumptions that it's making.